Welcome to Software Quality Now. My name is Steve, and this channel focuses on the development of high-quality, mission-critical software. In today's video, we're going to begin looking at the product quality model found in ISO/IEC 25010:2011 SQuaRE, the ISO/IEC standard for systems and software quality requirements and evaluation. This is part one of a multi-part series discussing the product quality model. SQuaRE defines two models, quality in use and product quality. These models define characteristics relevant to all software products and computer systems. These models have been decomposed into factors, with some factors further decomposed into subfactors. ISO/IEC 25012 contains a complementary data quality model. The quality in use and product quality models do not provide a recipe for software quality. The factors and subfactors are like a checklist or a cheat sheet. They're reminders used throughout the software development process to ensure that everything has been considered. Links in the description will take you to the videos in the SQuaRE Quality in Use Part 1 and SQuaRE Quality in Use Part 2 videos. In this video, we're going to begin looking at SQuaRE Product Quality Model. Product quality is decomposed into 8 factors. The 8 factors are functional suitability, performance efficiency, compatibility, usability, reliability, security, maintainability, and portability. This video will look at functional suitability, performance efficiency, and compatibility in detail. We'll look at the remaining product quality factors in future videos. Functional suitability is the first product quality factor. Functional suitability is defined as the degree to which the system provides functions that meet stated and implied needs when used under specified conditions. In other words, the system does what it's supposed to do completely, accurately, and without any extra steps or unnecessary input. It's pretty basic stuff. After all, if the system doesn't do what it's supposed to do, what good is it? Before I get to a more detailed discussion of this seminal factor, let me quickly define the 3 suitability subfactors: functional completeness, functional correctness, and functional appropriateness. Completeness is defined to be the degree to which the set of functions covers all the specified tasks and user objectives. Correctness is defined to be the degree to which a product or system provides the correct results with the needed degree of precision. Finally, appropriateness is defined to be the degree to which the functions facilitate the accomplishment of a specified task or an objective. Focus on the phrase meet stated and implied needs. The stated needs are those that the stakeholders explicitly tell you about. The implied needs are those that the stakeholders forget to mention, take for granted, or aren't aware of. The implied needs will be much more numerous, especially at the beginning of an effort. Remember, there are usually lots of different stakeholders with different needs, perspectives. These different stakeholders expect different things from the system. You must get into the mindset of the stakeholders. Become an advocate for the customer. In fact, that's one of the jobs of the software architect, but that will be covered in a future video. As far as the explicit needs go, can't we simply ask the customer for their needs, also known as requirements, and expect to get a complete and accurate set of requirements? Well, that would be nice, but it never works that way. Often, we get some solutions masquerading as requirements. Oh, they may be perfect, ready to be polished and implemented, but often they are naive, ill-informed, and unworkable. In any case, The needs hiding in those solutions have value, which must be teased out. As far as the implied requirements goes, that requires time, patience, and skill. How do you capture the requirements? Is a user interface prototype the right approach? What about stories or use cases? How about just building the system iteratively and incrementally? Well, these are all valid approaches, and they all work for certain classes of problems. Let me give you a real-life example. What if you had to provide a subsystem that calculated royalties for music publishing? I did it for a client, and this was some of the most complex logic I've ever worked on. Leave it to the extraordinarily successful musical artists and their highly paid lawyers to dream up complicated rules for the calculation of royalties. The engine that does the calculation didn't have a user interface and is implemented as a series of complex calculations with a lot of contingencies and decision points. How do you capture that logic in a form that you can use to implement a solution and subsequently test for accuracy? How do you have the customer verify your understanding of the calculations before you begin implementation? A common issue I see is the tendency to use a single technique for capturing requirements. After all, if all I have is a hammer, every problem is going to look like a nail. The techniques to use to define the functionality to be delivered must be determined early on, and you may very well end up using multiple techniques for any reasonably complex type of mission-critical system. By the way, for the music publishing royalty calculations, we made heavy use of UML activity diagrams to capture the contingencies and decision logic. Another common issue is the sheer volume of needs. There is a tendency to assume that a system must implement all the requirements to have any value. You should ask your stakeholders, is there some subset of requirements that can be implemented and delivered? This is called an MVP, which stands for minimally viable product. Once an MVP is delivered, it can start providing value, followed up by incremental deliveries providing additional functionality. Even if it can't be formally delivered and put to use, an iterative and incremental approach instills confidence, and it uncovers issues early and often. Performance efficiency, the next product quality factor, is defined as performance relative to the amount of resources used under stated conditions. Performance efficiency is an essential requirement of most systems in that they make good use of resources in space and time. Performance efficiency requirements should be captured as non-functional requirements. Performance efficiency has three subvectors: time behavior, resource utilization, and capacity. Time behavior is the degree to which requirements are met by the response and processing times and throughput rates of a product or system when performing its functions. One aspect of time behavior is user interface response times. A user interface that is too slow is obviously a no-go, but too fast can lead to issues as well. Another aspect of time behavior is how long it takes to process a transaction. That system I just mentioned about the music royalty calculations had to process files containing many millions of transactions in extremely short periods of time. That was especially a challenge given the complexity of the calculations. Resource utilization is another aspect of performance efficiency. Resource utilization is the degree to which requirements are met by the amounts and types of resources used by a product or system when performing its functions. Resources can include other software products, the software and hardware configuration of the system, materials, and even human resources. There is often a trade-off between resource utilization and time behavior. Returning back to the royalty calculations, you might initially assume that the best way to get those calculations done quickly would be to use a bigger, faster server. And that kind of brute force approach to performing the royalty calculations quickly simply wasn't acceptable, given the target hardware configuration. The key was a clever approach to doing the calculations based on a thorough understanding of the nature of the transactions and the calculations themselves. The third performance efficiency subfactor is capacity. It's the degree to which requirements are met by the maximum limits of product or system parameters. Capacity might include the maximum number of items stored, the maximum number of concurrent users, communication bandwidth, transaction throughput, and database size. Sometimes as engineers, we get carried away with maximizing performance. Increased performance efficiency often results in increased complexity. Unnecessary complexity should be avoided because latent defects are often found in areas of high complexity. Areas of high complexity are also likely to cause future problems for those folks doing maintenance and extensions. You don't get extra points for squeezing out unnecessary performance efficiency. I have always been a big believer in Donald Knuth's statement that premature optimization is the root of all evil. I architect and design my systems to make optimization as easy as possible after I've assured functional suitability. Capacity includes communication bandwidth. I worked on a line maintenance system for a major airline. Line maintenance includes all the maintenance activities performed on the aircraft at or near the gate between flights. Line maintenance personnel need to be constantly updated on flight status, even for flights at other airports. Issues often propagate through the system wherever the airline's planes fly. Now, this was about 30 years ago when some of the more remote airports presented a challenge. They used dial-up 9600 BPS modems over a phone system that was unreliable in these remote locations. The solution was required to ensure that flight status was delivered accurately and in a timely fashion, despite limited communication bandwidth at a small number of remote airports. The product quality factor of compatibility is next. Compatibility is the degree to which a product, system, or component can exchange information with other product systems or components and or perform its required functions while sharing the same hardware or software environment. The two aspects of compatibility are coexistence and interoperability. The subfactor coexistence is defined to be the degree to which a product can perform its required functions efficiently while sharing a common environment and resources with other products without detrimental impact on any other product. Back in the old days, this was a constant concern. I used to teach a course on the Unix operating system, System 5 actually, and the time-sharing aspects were an important part of this. Some of you may know just how nice that was. Get it? Nice? Okay, moving right along. However, this is even a concern in a serverless cloud environment. I built a file ingestion system that burst an incoming file into its constituent transactions and process those transactions in parallel using AWS Lambda functions. The solution, it could be blazingly fast, but sometimes multiple files might arrive simultaneously, or other work might need to be done using Lambda functions. There is a limit to the number of Lambda functions that you can run simultaneously. While you can request the limit to be raised, you still need to be aware of what functionality is running at the same time, or you may end up with things being a lot slower than you anticipated. The other compatibility subfactor is interoperability. It's defined as the degree to which two or more systems, products, or components can exchange information and use the information that has been exchanged. Interoperability also includes the ability to utilize shared services. Sometimes the systems we build must interact with legacy systems that cannot or will not be changed. In those cases, we must adapt to those systems. This was the case when I was building software for a health insurance system. The Pharmacy Benefits Manager, known as a PBM, exchanged data using flat files and FTP, not my preferred method of data exchange. At other times, existing systems can be changed. As I've mentioned previously, I built a system to mark the shells of eggs with freshness and traceability information using lasers. The software that controlled the lasers had been around for 20 years, ran in a different hardware and software environment from that being used for the rest of the system, and did not have a way to exchange data in real time with external software components. We made changes to its implementation to allow the exchange of data using queues, with an understanding that the implementation would be replaced at a future date, due to reliability issues with the original implementation. So, let's do a quick review. SQuaRE defines two models, quality in use and product quality. These models define characteristics relevant to all software products and computer systems. These models have been decomposed into factors, with some factors decomposed into subfactors. We discussed quality in use in 2 previous videos. We've just completed Part 1 of the product quality model, where we discussed the factors functional suitability, performance efficiency, and compatibility. We'll discuss the other 5 factors in future videos. This is Steve. Thanks for watching. Don't forget to like, share, comment, and subscribe so you don't miss any upcoming videos. Your support makes it possible for me to continue making these videos. See you for the next video on the Software Quality Now channel, where we focus on high-quality, mission-critical software development.